Hello, folks. Am I on? Not on? Hello, folks. Am I on? Can you hear me? Great. Well, I'd like to welcome you all. I'd like to welcome you all to the April meeting of the Delaware Valley Amateur Astronomers, being held jointly with the American Association of Physics Teachers of our region. So yeah, welcome. And if you're here with the teachers, raise your hand so we know who you are. Hello, well, thank you very much. My name's Jan Rush and I'm president of DVAA. First of all, we got some really sad news recently, which we have to talk about. We lost a really important member of DVAA on the 8th. Lou Varvarizis has just been a wonderful club member who has been really active in astrophotography. He really started astrophotography in this club, even before it was mainstream, before it was something that people were interested and knew very much about. He lived out in Green Lane, and he was the one who really identified the spot that we go for dark sky observing and helped us make that happen. So we are really going to miss him. He was only 54. He died way too young. Bill, I think Bill McGeaney was going to say a few words, right? Bill?
Put it on. Okay. All right. I wanted to just, I came across this quote and a Stephen Hawking quote: "To confine our attention to terrestrial matters will be the limit to human spirit." And Lou was an interesting character. He was someone who really, he had a lot of charisma, a lot of wit. He was dedicated to something, and when he got his mind set on it, he went to the nth degree to get it taken care of. And if any of you guys really went over to Lou's house, you could see this. If you went down his basement, it was a studio with almost every piece of equipment you need to create your own band. He was quirky, right? He had the rotary phone that they bought the landline for, that you could actually use, and it would ring. You look at it, like, I can't even remember how to use this thing. I'm sure we have members who don't even know, will look at it and not even understand how to use it. And of course, he dove into this astrophotography nonsense way before it became popular with most of us here. Back in 2015, I remember going up to Cherry Springs with many of you guys. I know one of my favorite memories of that is Jeremy and Gary Travazzano. They essentially formed what looked like a UN relief tent facility up there. But we had a great time up there. And
it's been defunded now.
Yeah, it's been defunded. What Lou was doing, he was doing deep sky astrophotography up there at Cherry Springs, and we were all pretty much in the basement. And then we saw the images he was taking, and when he started showing the club, it was all incredible stuff. And Lou was working on this stuff before we had ZWO streamline everything into one app, before we had, you know, all these nice devices that do pretty much everything that he had to do, with a lot of hours of frustration, a lot of hours of digging around and learning. And he was a friend. He was someone I remember during COVID. We did a lot of You Don't Know Jack games, and I know Jeremy, some of the other guys were were on that and learned that Missy missed her calling. She should have been a rap artist because she crushed us every time we had to do hip hop. And and you know, he was just someone who always he was always waiting for the punchline. To the point that he would, go the extra mile to really dive in, like I said, dive into stuff. So he got his whole house all configured to be a smart house. And every time Jeremy could interlude, Jeremy would try and insert a purchase order for small size condoms. We would have to quickly abort that order. But I'm gonna miss him. I know many of you guys are gonna miss him. He was a mentor for me on astrophotography. I spent a lot of hours over at his house with him and Missy and Woody, and he really kind of showed me the ropes of how to build my first rig, and and all the little troubles that everyone knows this in astrophotography, all the little nuanced moments that take hours of your life away just to figure out one stupid thing. And he was there to really help me solve those. So yeah, we lost Lou way too early, and know there's going to be a hole in this club. And just want to say it's good to know you, buddy. And yeah, hopefully, they have a lot of Russian crash videos up there in the afterlife for you.
Thank you. The family is holding a visitation on next Tuesday. And I hope as many of you who can come and show how much Lou meant to us in the club. It'll be from 5 to 9 at the Devlin Gotcha Funeral Home in Phoenixville.
It's 5 to 7.
What did I say?
5 to 9.
Oh, yes, 5 to 7 is the correct. Sorry. Thank you. Okay. So since we have some people here who may not know DVAA, we thought we ought to do a few words on who we are. So Delaware Valley Amateur Astronomers are a nonprofit, completely volunteer-run organization of amateur astronomers based here in the Philadelphia area. We are really people with very diverse occupations and training, and really are united by the one thing we love, which is astronomy. And that makes for a really rich, diversified group, which is fun to be with. The official mission of DVAA is to aid and encourage amateur astronomers in observation and scientific research projects, to encourage cooperation and the exchange of ideas among amateur astronomers, and to interest and educate the general public in the science of astronomy. So we have a number of public outreach activities. We have monthly star parties at Valley Forge National Historical Park. We have monthly astronomy-related indoor presentations. That's where you are tonight. We have star parties, solar observing, and educational presentations jointly sponsored with various community organizations. So scouts, libraries, schools, universities, and we also have outreach youth awards. I'm going to tell you a little more about those in a minute. For those of you who are members, we nurture each other in dark sky observing and astrophotography. We hold how-to clinics with telescopes, binoculars, and imaging. Astrophotography workshops. We have telescope rentals for $10 a month. So you can rent a scope just to try it out and see if you like it. With we have different varieties of scopes, and we take trips together. We have astronomy-related bus trips. So our specific upcoming events are, and this is of interest to a lot of you, I know. First is going to be the weekend we have booked in Cherry Springs at the Big Dipper and the Little Dipper lodges. There are still 4 beds left in the lodge, not bedrooms, but just beds. And but they're in a room, don't worry. Yes.
Just so everyone's aware, there's one queen size bed there.
Uh-huh.
So if there's a couple you can have, there's, it says 4 beds up, it was like. Just wanna allay that.
But it would be a couple who was staying with other people. Yeah.
Yeah, I mean, it was a small twin.
Yeah, or you could share it with Bill.
Right. Okay, and then the camping spots, it's a very big spot to camp, so the camping spots are unlimited. You can wait until you see what the weather's gonna be before you sign up for camping if you like, because there is unlimited room. And if you're camping, what your money pays for is use of the facilities, the shower, the toilet, the kitchen, and a place to warm up and place to recharge your devices if you like, and commune with your fellow astronomers.
It's a very nice place to observe from too.
Yes, it is. It's a very nice place to observe from. And it's just us, no crowds, just us. Okay, on May 3rd, we have our next public star party at Valley Forge National Historical Park. And up on the table over there where Joe and Scott are sitting, there's a schedule for all the upcoming star parties. So pick one up as you leave here, if you'd like to know when all the future dates are. On May 9th, we have May 7th, we have the monthly astrophotography workshop via Zoom. May 9th, we'll have our monthly meeting here. May 17th, we are announcing a dark sky observing clinic for members. So this is our how-to clinic outdoors. It'll be at Green Lane, and I'll tell you a little bit more about that in a minute. Then we have an outreach event, a Girl Scout camp in Gilbertsville. This is a nighttime event, and Ken Kopplinger is in charge of this, and he's asking people to show up with their scopes because there are about 200 Girl Scouts. So we'll need probably, I would say, at least 5 or 6 scopes to service them well. So if you can participate in that, give Ken an email at outreach@dvaa.org, sorry.
Call them on the rotary phone.
Yes, and May 31st, we have another outreach event at Radnor. That's being led by Barry Johnson. And that's the Great American Campout, which is an event where they teach kids about camping, and we set up telescopes so they can see the night sky while they're getting ready for their evening. We really like to support this event because Radnor gives us this wonderful facility to have our meetings in. So we have a nice symbiotic relationship with Radnor. And this is one of the events that we always support with them. So let Barry know if you can come and help out at that. So we need some telescopes for that as well. There'll be about, I'd say, 75 people probably is the usual enrollment for that one. Okay, Dark Skies Telescope Clinic. Many of you have been asking, when can we have our next outdoor clinic? Well, we scheduled it for Saturday, May 17th with a backup date of May 18th. And if you want to come, this is for members only or their immediate families. If you want to come and bring your telescope and have one-on-one help with that, you are very welcome. We need you to register for it because during the registration process, you'll be asked questions about what you're bringing, what type of telescope, so we can make sure that there's someone there who knows how to operate your particular telescope and can mentor you one-on-one or 2-to-1 or 3-to-1. It's usually 2-to-1, I guess. Very close help or very close mentorship. So that's open for registration. So when you go home tonight, if you'd like to come to that clinic, sign up for it. Now, because we have all of the teachers here, we wanted to tell you a little bit more about the DVAA Youth Awards. And this is something that has been originated and spearheaded by Al Lamperti. There's a button on the home page of the website that says Youth Awards Program. And if you click on that, you'll get all the information you need. And this is one of last year's winners. This is Daniel Adibi. And he's giving his presentation to us of his research. I'll tell you, these kids are doing very impressive things. They aren't really kids. So the first place award last year was Daniel Adibi, and his research project was differentiating characteristics in exoplanet host stars. Second place winner was Iftikhar Taruno, effectiveness of calculating the redshift of quasars photometrically. Just to give you an idea about how exotic these, or how incredibly these students are. And third place was Elise Olmsted with pulsar nulling. So those were last year's winners. I think the deadline is May 31st, is it? Is that right? Oh, May 1? Okay, I probably have it on another slide. But if any of you teachers have a student that would like to participate, somebody who has a project that they worked on maybe for a science fair, we would love to see their work. And we will, it's very inspiring just to have these kids present and tell us what they're doing, because these are the astronomers of the future that do this kind of work. Okay, the judging criteria are on scientific methodology, clear and focused purpose, and a good hypothesis, data collection and analysis, and the clarity of their presentation. So submissions need to be sent electronically before May 1st. And you send them to youthawards@dvaa.org. Anything else you'd like to add, Al? Okay. All right, now we'd like to hear a little bit more about what the American Association of Physics Teachers is all about. So Jeremy's straddling both organizations, so he's going to tell us.
All right, got to switch hats here. All right, let me close this down. I'll bring up another presentation. Yeah, Ryan couldn't be here tonight, so he kind of deputized me to come out here. So I'm the very past president, I think. Let's start this up. Yes, this is the beginning of the 2025 meeting of the American Association of Physics Teachers, Southeast Pennsylvania section. So it's starting tonight. We'll have a presentation this evening, but the main part of the meeting is going to happen tomorrow at Drexel, starting at 8:30, bright and early. So we'll have several different talks. We'll have Phil Nelson from the University of Pennsylvania. We'll have Christy Love, who's also giving a presentation tonight. And then we'll have some contributed talks, demos and posters and a few other things. I'm giving one of them, so well, it'll hopefully go uphill from there. All right, so a little bit more about who we are and what we do. Gotta activate this first. There we go. All right, so we're the Southeast Pennsylvania section of the AAPT. So the AAPT is a national organization of physics teachers at the high school and college level. And SEPS is our regional organization, which basically covers the 5-county region surrounding Philadelphia. So the AAPT is a professional membership association of scientists dedicated to enhancing the understanding and appreciation of physics through teaching. This at both the high school and college level. They do 2 annual conferences every year. These are great conferences to go to if you're in physics education, but they do involve a lot of travel. It's generally about a week away from home, so hotels, airfare, all of that sort of stuff. So they have workshops on physics teaching. People give presentations, also supporting a very, very bad word, DEI initiatives. They've job postings, various publications. They have guidelines for evaluating curricula, which we use very heavily because we recently updated our curriculum at Villanova. Awesome. And other things. So the Southeast Pennsylvania section basically gives a lower barrier to entry. So it provides local connections to other teachers in the area. And we hold local conferences. We typically have 2 meetings per year. So it is a mixture of high school and college folks. I put 50-50 there. It's kind of a placeholder. It's gone up and down over the years. At times we've been primarily high school, other times predominantly college. So it kind of goes back and forth. So we do hold 2 meetings. So we have a formal conference. Historically, that's been in the spring. We did switch that a little bit up during COVID, but we're back to spring meetings now. That's what's happening at this point. And then in the fall, we'll do a demo day, which is usually at a high school. And that's usually just people come in and show off some interesting stuff that they've been working on. Occasionally we'll do workshops. We do have a pretty active email list, so we have job postings in the area, discussion forum. We'd like to get it a little bit more active, but it is there. And here's the best part: membership is $10 a year. What can you get for $10? I should have updated the year there. So our president is Ryan Batke at UPenn. You could tell I've used this a few times before. Our VP is Kathleen Hennessy. She's at St. Joseph's Prep. Our secretary is Shindu at Widener. She's actually getting married tomorrow, so that's why she's not at the meeting. Our treasurer is Mark Barron. He'll be at the meeting tomorrow to collect everyone's dues. Section rep is currently vacant, so we'll be holding elections tomorrow to fill that. Our immediate past president is Paula Miller at Abraham Lincoln High School, and our webmaster is Mark Scaponis, who's at Gwynedd Mercy. And that's it for SEPS. So hopefully you learned a little bit about our organization, and hope to see the physics teachers tomorrow at Drexel. Thanks.
Okay, now we'd like to hear from Brian Lee, our welcoming chair, about new members.
Hello, my name is Brian Lee. I'm a welcoming chair for the DVAA. We have 7 new members this month. Keith and Roberta Lucas, Michael Horowitz, Bob Doherty, Vian Arden, Roberta Shaner, and John Hoka. So please welcome them.
Is anybody here for the first time tonight? Welcome. All righty. I just need to ask if anyone else has any announcements they'd like to make before we go to the rest of the program. Yes. Oh, yes. How about, could you come over here and, or do you want to take the mic over there?
Hi, everybody, I'm Joanne, I'm the Reynolds chair, and tonight I brought along that's fifth week CSAR for your consideration, and also we're mounting it equatorially. That seems to be in fact among CSAR users. So anyone who's interested, please come and see. Thank you.
A lot of you have already taken advantage of our sales table over there. But please, we're going to have it open after the meeting, so you're free to go and take a look. If there's something that you've been have your eye on, you think it would work great with your setup, but the price is a little too high, Scott says he's willing to entertain other offers.
And basically doesn't want to take any of the time.
I don't.
Right.
And we have a good selection of books there too for $1, so that's a deal. So feel free to take anything you like for $1. Okay. Now I'd like to introduce Jeremy, our programs chair, to introduce our speaker for tonight.
I get double pay for tonight, right? All right, so this is always a fun meeting that we have the physics teachers together with the astronomers. So it's always an interesting challenge to find a speaker who will be give a relevant talk to both groups. So I'm pleased to say that we found basically the perfect speaker for tonight. We're very happy to have Dr. Christina Love. She is an associate teaching professor at Drexel University. She did her PhD in physics at Temple University. Prior to that, she did her BS in physics education at Westchester University. Been a local around here. She also did a postdoc for the Transportation Security Laboratory looking for explosive detection. which is a little bit different from her original field, which is dark matter detection and cosmology. So currently she's a member of the IceCube collaboration. She's the creator of something called Name That Neutrino, that we'll hear about. Very heavily involved in various citizen science initiatives. She's a co-founder and the Drexel head of the High Altitude Engineering for Research in Astrophysics, or HERA collaboration. She's also involved in Start Talking Science. And, has received numerous awards for teaching and outreach. So please join me in welcoming Dr. Christina Love.
Since the camera's over there, you would have to
Okay,
stand
sure.
here to be in view of,
Yeah.
yeah. And you turn it on,
Okay, fine.
on the. Yeah, this is- Great. Is this one? Yeah, that's good. No, should be on. Yeah.
Can you hear me?
Yeah.
Is that good? All right.
All right, let me open up your slides again. Here we go.
Perfect. Thank you. Thank you so much for that introduction and thank you for having me. I'm really excited for this group. I think, yeah, it's a perfect intersection, conveniently, for me. So yes, I work on something called IceCube, which is this particle detector at the South Pole. And then I developed the idea of having a citizen science project for it. Isn't working. Oh, just kidding. All right, so I wanted just to give some credit to my students who have had so much impact on this project. One of them is Elizabeth Warwick, who is now getting her PhD at the University of Alabama. Andrew Phillips, who unfortunately, fortunately has a job now at Lockheed Martin. And so he graduated with his bachelor's in physics and went on to work at Lockheed. And then Maddie Lee, who is currently working on her bachelor's in physics. So these students spent a lot of time on this project because they earned their thesis and they wrote something up about it and gave a presentation and everything. But I've also had like a lot of other students working on this project over the past 2 years. And the interesting thing I think about this is that I have students from different fields. Okay, so I have some students maybe from biology who get involved, some engineering students who also get involved. I even have a high school student who has been working on the project. And so it's interesting because the idea of citizen science is to get anyone involved. And so one of the things that I'll talk tomorrow about is how I have expanded my group to have so many students and such a variety of students as well. They don't have to just be from the physics department. Okay, why what are we looking at here? Anybody know? What's one of these images? X-ray. We've got an X-ray right here. Yep. This is an MRI. That's a hard one. Yep. And then what is this one? Visual. Yeah. So we know that there's different ways to look at a hand, right? And when we look at the hand in different ways, it gives us different information, right? We're able to see the bones more, the heat signature here, the muscles, right? The skin, fine. And so we know that we can do this in astronomy as well, right? So this is looking at different parts of the electromagnetic spectrum of a galaxy. So this is called the Whirlpool Galaxy. This is visual. This is optical. So this is what our human eyes can see if we were to look in just an optical telescope. But we can look at different parts of this electromagnetic spectrum, light in a different way, where you see different parts of the galaxy glows in these different parts of the electromagnetic spectrum, right? X-ray is looking very different than radio over here. Actually, all of them are looking quite different. And so we learn different information, right? The fact that we're able to do this. And so what I want to motivate for you tonight is the idea of, instead of using different parts of the electromagnetic spectrum, IceCube uses the concept of using other particles, other things to look for in our sky. And so this right here is kind of like the periodic table for physics, for particle physics. This is our our best story of everything. And you probably will recognize the electrons, right? So we know atoms are made of protons, neutrons, and electrons. And so that's a fundamental particle, right? It can't be broken down into more parts. And another thing that you might not recognize are quarks up here. And so quarks are what make up protons and neutrons. Okay, so protons and neutrons are not fundamental. They are instead made of quarks. And so that's what we have here. The thing that IceCube really hunts for, though, are called neutrinos. So neutrinos are just another part of this puzzle. They're these particles that are fundamental, okay? And they can give us maybe some more information, just as other parts of the electromagnetic spectrum can give us more information as well. So there's a lot of neutrinos even in this room right now. And in fact, if you just think about your thumb, you have about 65 million neutrinos passing through your thumb every second. And so they are so abundant. We have so many neutrinos. But of course we can't feel this, right? It's not noticeable to me. It doesn't hurt or anything like that. And so they're rarely interacting. And in fact, neutrinos primarily interact via the weak force, which is called the weak force because it's weak, right? So it's hard to detect these particles. But the other cool thing about neutrinos is they're kind of mysterious. So you saw there were 3 different flavors. They do this weird thing where they turn into each other, and that this active area of research called neutrino oscillations. So there's just like a lot of really rich things that we can learn about neutrinos in addition to using them for astronomy. Okay, so this is kind of a new field of astronomy called neutrino astronomy. And so we know that normally you go out and you look at the sky with your eyes and you see stars. And so that's visible light, right? Or maybe if you have a fancy telescope that can look in other parts of the electromagnetic spectrum, you're still using light, right? You're still using X-rays or gamma or something like that. But so this whole concept is that we're gonna use these neutrinos that we're gonna try to detect, that we can detect at the South Pole. And we're going to use that to understand something about astronomy, kind of tying these things together. And part of the motivation here is what's called really also like multi-messenger astronomy, which is kind of a new field in the sense that you have some sort of like extreme event happening, maybe merging of black holes or a supermassive black hole, merging of neutron stars. Something happens and all these different kinds of messengers are sent out. And so one of them that's been in the news a lot, over the past, 5 or 10 years are gravitational waves. And so that's one messenger, one thing that you can measure. Another thing is called a cosmic ray, but cosmic rays are charged. And so what that means is that they're going to bend when they get near magnetic fields. So they don't exactly point back to their sources, right? We don't know where they necessarily came from because they bent in these magnetic fields on their way to the Earth. Neutrinos, on the other hand, first of all, they're going to travel in a straight line. They're neutral, but they're also hard to detect and rarely interacting. So if you happen to detect it, then you can be confident that you're the first one to see it, right? It hasn't been detected before that. And so we built this detector actually probably 15 years ago at the South Pole. It's called IceCube. And so I just want to orient ourselves a little bit to think about the South Pole. So this is Antarctica. We're looking at the bottom of the Earth here. And actually, while I do this, maybe I also want to show you this jacket. Oh, I'll go back over here. This jacket that we got from the South Pole. So this was used at the South Pole. So it's been to Antarctica. And it's, I'm just going to pass it around actually, because it's kind of fun to see how heavy it is. You can try it on if you want. But so this is the kind of gear that they have to wear because it is so cold, right? You know that it's cold at the South Pole. And in fact, I was just on a call this morning with our winter overs who are staying the entire winter, the South Pole winter. So that's now. And they were saying that the warmest they think it's like ever gotten is 0 degrees Fahrenheit is the warmest it's ever gotten. So it's really, really cold there. Regularly negative. 40, -50. I think the coldest it's gotten is -80, kind of recently, actually, Fahrenheit. Okay, so we're in Antarctica. It's really, really cold. We're at the bottom of the Earth here. And the South Pole is, you know, kind of towards the middle of this continent. And so it's a continent, which means it's like got a, you know, bedrock, like it's ground. But on top of the ground is this glacier, right? So we have glacial ice on top of that land. And so we have actually movement of the entire glacial ice. So this is the South Pole. This is one of my collaborators who recently graduated from Drexel. He got to go to the South Pole. I have not been to the South Pole. I'm still working on getting there. But the funny thing here is that because the ice sheet itself is moving, the South Pole that we like stuck in the ground moves and is no longer at the geographic South Pole. So every year on January 1st, the people at the South Pole Station have a pole moving ceremony where they actually then put the pole in the right spot where it is actually at this, you know, the spin axis, the geographic South Pole. Ish. So this is why we built Ice Cube there, though, is because of this ice sheet, because of this glacial ice. It turns out it's super, super clear. And so what we can do is use that ice as a detector medium, as like our target, that a particle will come and interact with the ice. When it does that, it actually produces this light signature. And so what we did was put over 5,000 of these light sensors into the ice. All right, and so this is, it's called a digital optical module. We call it a DOM. I'm very echoey right here. And so these are the things that can read out the signal that is produced when the particle interacts with the ice in our detectors. It's a gigantic, actually, I'll say it again. Yeah, I said this morning. Ice Cube is currently the largest neutrino detector in the world. There is another one under construction, but it is yet to surpass Ice Cube. It will when it's finished. If and when it gets finished, it will. That you might have heard of in the news lately is called KM3net, and this one is built in the Mediterranean Sea. So Ice Cube is still the largest, and in fact, it's a kilometer by kilometer by kilometer, which in a nice, easy visual way, it's 3 Eiffel Towers tall, right? So it's very, very large. It's about a kilometer down because we wanted to find that clearest possible ice that we could get to. And so, yeah, this is the Ice Cube lab then, which is sits up here. So this is, a regular size building, I'd say. These are the people. And to put it in perspective, right, 3 Eiffel Towers tall compared to this building where these people are. I just wanted to kind of point that out. And then of course, this is one of those like bubbles that you see in here. One of these bubbles is corresponding to one of these 5,000 detectors. So we can wrap our heads around that a little bit. And so this is not to scale. This picture is not to scale. We do not have supermassive black holes this close, but the idea is that, okay, there's something out in the universe producing these neutrinos that then can travel to us, and then we can detect down here at the South Pole. So in Ice Cube, we see 2 basic kinds of shapes. We have a model over here, sorry. Yeah. Wonderful. 2 basic kinds of shapes of light signals. Remember, the particle comes in, interacts with the ice, and then produces these light patterns. And so one of them, we call it a cascade. It's kind of like a bubble shape that kind of grows outward. So it starts in the middle and then grows outward in a spherical way. And the other kind of signature that we have is like a straight line. So we call it a track. And the color here, I should let you know, corresponds to the time. Like, when did we see the signal? When did we see the light? And so it's in Roy G. Biv. Of course, we would pick that. So red is first, and then orange, yellow, blah, blah, blah. And then blue, if you see blue, that's going to be towards the end, or violet. And so depending upon what kind of neutrino you have, we have those 3 flavors in the beginning, those 3 different types of neutrinos, and then they can have different types of interactions via the weak force again, but this is why we would get these different kinds of signatures. So I want to just kind of play this. Okay. To show, this is like a simulation showing, the red arrow is supposed to be signifying, that particle, that neutrino initially coming in. And then this is how the light signature then looks. And you can kind of see the signal growing, the pattern growing here. So this is a track. We see the red, okay, we don't normally see the red line going through, right? This is just from the simulation. But you see here that this signature, this signal is happening in a straight line. And so this is a track that we would describe. And then the next one will be a cascade, where it's more so about like a localized interaction that then the light is spreading out towards the sides. Oops, that's a spoiler. Okay, so here's the Ice Cube collaboration. It's made of, over 350 people across the entire world. In fact, we're in 14 different countries and 59 different institutions. And so, yeah, so as I was showing, whoops, that's me. This is the Ice Cube collaboration meeting that we had. This is us here near Philadelphia. And so, this isn't even everybody, but we have these regular meetings where we can get together and share our work and make sure that, that we're all working together, because it's difficult when you're in different locations, in different time zones, in different languages, right? So this is a really quite challenging kind of atmosphere. I'm talking mostly about neutrino sources, the fact that we can use neutrinos to kind of give us a picture of the sky, give us more information for astronomy. But we actually do a lot of different kinds of studies as well. We look for dark matter, we study cosmic rays as well. And then there are some groups doing like neutrino oscillations or even sterile neutrinos, which is like a new flavor of neutrino, new kind of neutrino. We're doing all sorts of things like that. Not all of these people are at the South Pole, right? And in fact, right now, 2 ice cubers are at the South Pole, and that's it. They are staying for the entire winter, the South Pole winter. I think they stay for several months. And so that's why we only have about 40 people at the South Pole station in the winter. In fact, I think it's 42, they said today. And then more like 150 people in the summer. It gets, slightly warmer, but the sun is up is the other thing, right? And so, so when they winter over, there's no planes, right? There's no planes whatsoever. And so they're there. In fact, I think a couple years ago, they did do a medevac where someone, required some assistance to leave. It was like an emergency, but what ended up happening was, I think, it's a dangerous situation. It's really cold, it's really dark, it's really windy. And so, I think it was fine, but it was like not as successful as they thought it was going to be. The pilots were struggling. And so the other thing about Antarctica is, we know there's penguins there and in Antarctica, but they're on the coast. Okay, so at the South Pole, which is in the interior of Antarctica, there's no native plant or animal life. There's no trees, there's no penguins, there's no bugs. And of course now there's people, right? So we have about 47 structures, and there's really like 5 scientific experiments going on at the South Pole, Ice Cube being just one of them. We're working on adding more of these detectors right now. It's called Ice Cube Upgrade. And so we should be finishing in the summer. We only do this work in the South Pole summer. So this coming Northern Hemisphere winter. And so what we're doing is we're drilling more holes to add more of these detectors on strings. We're adding 7 new strings. This up here is an artist renditioning of like what it probably looks like if you were able to be in the ice and look at it. So one of the interesting things about how this detector is built is that we have to melt the ice, and that's how we get the detector down, and then it refreezes, right? And so then they're there. Okay, so the ones that we've already deployed are there, and we don't plan on going back and fixing them if they needed to be fixed. And so so in fact, it's kind of like a really long-term kind of commitment. One thing that we often say, I think, in everyday life, we say northern lights, okay? But yeah, we can also have southern lights. So northern lights are aurora borealis, southern lights are aurora australis. And it's, we know it's because of the magnetic field from the earth and the solar wind coming towards the earth. And so, yeah, we get aurora in the north and in the south. we just have more land mass and more people living in the northern hemisphere. And like, I guess that's just where we are right now also. But these are some photographs of what the aurora can look like at the South Pole. So really, really quite beautiful. This is outside my house, actually. I just had to brag about when this is just over in South Jersey in October. I'm not sure if any of you got a chance to see it, but it was really quite amazing. Okay, so there's really like 2 days that they have at the South Pole. One really, really long dark night and one really, really long, or one day, I guess, right? What happens here is that we have, just because of the Earth's tilt, right? You have a scenario where the sun never sets. So this is the summer at the South Pole. The sun never sets. And then the other scenario is when the sun, whoops, never rises. So it's just so dark for months and months on end. And in fact, the sunset, kind of like the twilight looking sunset, lasts for like about a week or 2 in that transitioning time in between just totally being up and being down. Oh. Okay, another common misconception is that there's a lot of snowing happening at the South Pole. And in fact, it's a desert. It's really dry and yeah, it's cold also, and it's really windy too. But the amount of snow that is actually falling from the atmosphere is just a few centimeters per year. And so what ends up happening is you get snow drifts though. And so there are like piles of snow that appear maybe overnight, and it's just because of the wind and because of the snow moving around on this top layer. And in fact, we have what's called ice top, which is some detectors on the top here that's been buried by several feet of snow drifts over the years. One of the most interesting discoveries that we've made lately is related to the Milky Way, our galaxy. And so if you're lucky enough to get to a nice dark sky, you know that you would be able to see this Milky Way, right? Our galaxy, we're looking out into our galaxy. And if you had a nice camera or telescope, maybe you were able to see something more like this. And so we can kind of slice this as a rectangle and rotate it and look in different parts of the electromagnetic spectrum. And in fact, you know, researchers do this all the time. And so there's radio, here's optical, here's gamma. And the thing that we were able to do, we published this in Science in 2023, was to see the Milky Way in neutrinos. So this was that idea that we can now take a different image, right? We can now use a whole different tool to study the universe. Okay, I have a cool video that actually my student made. Whoops. Before you do that. Oh, it's kind of quiet. It's just music. Oh, there you go. Does that work? Yeah. It's just music. So this is this kind of dramatic astronomical event that might produce neutrinos. Okay, so we could imagine neutrinos being produced from this sort of event and traveling throughout the universe, rarely interacting until they make it to our detector in the South Pole. So we don't really have an Eiffel Tower there. That's just to help you understand the scale, right? But these like blue lines are the light being produced by these particles. It's called Cherenkov radiation. It's where the particles actually moving faster than the speed of light in that material in ice for us, like a sonic boom for light. And so there you saw a track. This is really like a cascade. So it's the particles growing outward. And then there's a dome. And so we're going to zoom out, right? Just like one of these. zoom out to all of these different strings, and then be able to zoom out all the way up to the top. So this is where, you know, we walk at the South Pole, and there's the Ice Cube Lab where all of our electronics are housed, and there for scale are celebratory humans. Okay, so yes, citizen science. So April is actually Citizen Science Month. I've like completely lost the mouse now. What am I doing? Is to the left or to the right?
To the right.
Oh, same thing. Opposite of anything I think. Okay, I found it. Okay. So citizen science is based on the concept that there's like wisdom in a crowd. So if you ask a lot of people how many jelly beans are in this jar, sure, you would get some people saying way too many, or way too few. But if you surveyed enough people and asked enough people, you would get like a distribution. And the average here would be near the right answer. Okay, and that's the concept of citizen science, is that we as humans are able to contribute in these kind of very unique ways. And so I'd like to talk about these two really cool examples of citizen science. One was back in 1715, Edmund Halley of Halley's Comet was trying to understand more about the eclipse that was happening at the time. And so he asked people a request to the curious to observe what they could about it, but more especially to note the time of continuance of total darkness. So he actually then collected people's observations of like how long did the total darkness, did the shadow last for where you were. Another really interesting, totally different perspective is this biology citizen science game that was a game. They really gamified it. It's called Fold It. And they were looking for protein structures, so how proteins are folded. And the really interesting thing that was a discovery from that project is that the shapes and the things that the citizen scientists were able to come up with were different than what the computer and the machine learning algorithms were coming up with. It was just like fundamentally different. And so it shows just like how rich and how important citizen science can be. And so my project named that neutrino lives on what's called Zooniverse. Zooniverse being this largest web-based platform. And so they have over 1 million different volunteers worldwide. And the idea is, it could be any kind of impractical research, and actually anyone can post their own project. So it doesn't have to necessarily come from a university or anything. And I think the most, one of the really basic ideas is like maybe a biology example of like bear migration or something. I don't even know anything, but you can take pictures, right, in the forest and ask the people, is there a bear in this picture or not? And that's fast, right? And that's easy, and anybody can do that. But actually, the image processing required for a computer algorithm to be able to read in and decide if there's a bear there or not is really time consuming and complicated, whereas a human can very quickly say if there's a bear or not. So that's one of the kinds of reasons why you might want to do this. You've all probably heard of Galaxy Zoo, which is kind of Zooniverse's most famous, longest running citizen science project. It's been running for over 17 years now. They have over 400,000 volunteers. But I think the really interesting thing for me is the amount of science that they've been able to produce from this project. And so they've published almost 80 different peer-reviewed research articles about the things that they're learning from the citizen science project. Right, so it's really about the richness of what can we learn. So this is where Name That Neutrino is right now. We've gone through like a first launch in 2023, and we're currently undergoing what we're calling our second launch. We right now have 3,700 or so volunteers registered, but together they've produced over 200, almost 300,000 classifications. So they've gone on and looked at one of our signals, right, for those light patterns, and decided the kind of category that it could belong in. One of the other cool things about IceCube is that because we're an international collaboration, we do have so many collaborators from different countries who speak different languages. And so we translated Name That Neutrino into we started in English. We translated it into 6 different languages, making it 7 total. And so really we have, okay, Google Translate can do something, but the idea is that we have IceCube collaborators who understand the science, who understand, those nuances. What was it? Oh, we call one of we call something skimming, and the Italian collaborator or the Italian translation kept calling skimming like coffee creamer over and over again. So in fact, this is what we ask. Skimming more so in our case, though, we mean on the sides of our detector, like not giving us really enough information, only just skimming the sides. So that's this category. And then we have the cascades and the tracks. The idea that it's more spherical shapes is a cascade, or a track is more like a linear shape. If you pick a track, then you can pick 3 different kinds of tracks. And so this is where it gets a little bit tricky, I think. I think the easiest one to recognize is called a through-going track. This is where just the line goes straight through in any direction, goes straight through the detector. But there are other options. One being a starting track, which actually turns out to be really important because a starting track is kind of like the smoking gun for neutrino interaction. So it's like the neutrino interacted right here, and then we were able to see the light signature come off of that. These through-going tracks or even these stopping tracks could be from background signals that we're not interested in using, right? We're looking for neutrinos instead. And so that's part of the reason why we need to be able to classify and like distinguish between these different kinds of signatures. And so why would we want to do this for IceCube? And so we do have excellent machine learning algorithms. And in fact, we use what's called a deep neural network. So that's what I mean by DNN. And so this is trained on, millions of simulated events, and it's able to predict things really well. But of course, we all know that there's some limitations to machine learning algorithms or limitations to artificial intelligence. And so here, this particular signature is going to, I think, be kind of obvious to you. We have noise. Okay, there's these kind of random bubbles all around, but we see this like clustering over on the side. So this is a skimming. I think we would agree. And in fact, our name that neutrino users agree that this is skimming. This is on our edge of our detector. It's not really giving us enough information. But for some reason, our machine learning algorithm, our DNN, thought that this was going all the way through, just straight through, kind of like slicing through like the main part of the detector, where a through going would be more like this, or like this, or even this, but not located on the edges as a skimming is here. So we see that, okay, we can maybe kind of maybe outperform like a machine learning algorithm. And so this is the result of our first launch. And so let me take a second to explain what's happening here. This is called a confusion matrix. So on the x-axis here, I have the 5 different categories for what the machine learning algorithm thinks. And then on the y-axis, I have those 5 different categories for what the citizen science users think. And so when we look in this top left corner, this is saying, okay, the machine learning algorithm is saying it's a skimming, and so are the users are saying it's a skimming, and we see it's 65% of the time, there's like an agreement. The cascades were a higher agreement, 92. We were seeing a lower agreement here between starting and stopping. What's probably more interesting, though, is when there was disagreement. Okay, so this is when the machine learning algorithm said starting, the users were saying through going, or when the users were saying skimming, the DNN, the machine learning algorithm, was saying through going. So there's some disagreement, some confusion here between who is right. And so what we decided to do was take these disagreeing events and look at them at like the expert level. So my students and I looked, and we all kind of had these conversations and all came up with our own classifications. And what we have is these results that we actually published in this European Journal of Physics, that the expert category was agreeing with the machine learning algorithm for starting and stopping tracks, whereas the through-going tracks were agreeing with the users much better. So it looks like the citizen users were better at identifying a through-going track and struggling with the starting and stopping, whereas the machine algorithm was able to kind of figure that out. And so one of the interesting things about citizen science is that you can look at this data in a lot of different ways. And so this is what what we call user confidence. And so it's like, how much are these people agreeing? So there's a retirement limit, which means each video is shown to multiple people. Okay, it's not just one person deciding, it's like, you know, it's democratic here, where we have maybe the first time we tried just 15 people, then we added 5 more people, then we added 5 more people. And so we were trying to see, is there some more agreement between the people? The more people we add, are they starting to agree more? Are they starting to like understand this? Because if you just ask 2 people, that's, you know, that's not really a great survey, right? You want to ask more people. But the thing that we were noticing was that there was not a lot of agreement. And in fact, we were kind of peaking around like 40-something% or 50%. And so you know, if you put these people in a room, they would be really angry at each other because they're not agreeing on the same thing here. And so that led us to look at the data in a different way and come up with a relaunch. And so that's why we talk about like our second launch. This though was really helpful to us to understand what should we include in our relaunch. And so the other thing that we realized was that actually the DNN was doing a pretty good job. And in fact, this is what's called like a reliability diagram, where this is how confident the DNN is saying. So it's like, oh, I'm 99% sure that it's a cascade. And it turns out actually it was 99% of the time correct then if it was confident. So it was interesting that it knew when it was right. It actually kind of knew when it was wrong. So this is scaling that, like if it's saying I'm not so sure, yeah, it's not so correct either. So it's able to predict whether it's accurate or not. The flatness of the yellow line here is interesting because the users don't care if the machine learning algorithm is confident or not. The users kind of steadily stayed at the same accuracy. And so that means at these low values of DNN confidence, that's where the users can outperform the machines, right? This is where we should target this. Because we need help. Our machine's not getting it over here, and so our users might be able to help them out. So we targeted these lower confidence values for our second launch. And so that's where we are now. And so when we look at the machine learning algorithm versus the truth label, so now we're able to look at our simulation in more detail and we don't have to use our expert by eye category. We see that like there's not a lot of diagonalization going on here, right? But we do see actually that our users are able to maybe outperform the machine learning algorithm in this second launch, this second iteration that's running right now. So this is just our preliminary data that we've seen so far. But the other thing that we can look at is kind of classification level information. And that means, and actually one of my students he's a mechanical engineering major and didn't even ever take an advanced physics class in his life, looked at our data and was like, well, wait a minute, I can tell you how long these people are taking to classify. Like it records the time that they open the video and it records the time that they click the button. This is what it is. And what we were seeing here, this is like just a few seconds. This is like, I opened the page and I just pushed the button, right? I hardly even thought. And in fact, my students, we had a race. We were like, how fast can you classify this? Does this even make any sense? And it's just really not possible because it's just too much to think about at once for you to be able to do it this quickly. And the other thing is that if you're not even watching the video, it's hard to be able to decide what's happening. And the video itself is 6 or 7 seconds long. And so this is what we're actively working on, kind of trying to clean up this data at this point, be able to find that maybe like maybe my 9-year-old son got a hold of my computer and just started randomly clicking on things, right? We can weed this data out, right? And make sure that we're looking only at the people who have actually watched the video, right? Spent more than half a second thinking about our question. The other thing that I wanted to let you know is that, okay, this needs people. We need people to do this. And so there's a couple different ways that I've done this. Zooniverse itself, has 1 million users or so already. But the other thing that I really want to tell the high school teachers in the room is that I've developed some high school like materials. It's like a crossword puzzle, like a slide deck to kind of give this like as like a little lesson in school where then students can then classify, you know, as like an activity, as like a lab, if you will. The other thing that I did was I was on KYW News Radio talking about this. So I reached out to the local media and said, hey, I'm doing this project. Wouldn't this be cool if you talked about it? And so they interviewed me there. We have, 300 people in our collaboration. So we reached out to them to then spread the word to maybe their friends and family, or also their institutions, or also their local media. And then there's just some cool social media posts. So actually IceCube is really, really active on social media, really like all of the platforms. So if you're interested in that, make sure you say IceCube Neutrino Observatory. Otherwise you end up with IceCube the rapper. That is the first thing when you've got 1 million views or something. So you're not gonna, anyway. And then, you know, outreach events. So we're working on making more changes. And so the idea, kind of the long-term goal for Name That Neutrino is to be able to have this like clear-cut way of saying, should this signal go to the machine learning algorithm, or should it go to the citizen users? And with that, you play to the tool's strengths, right? You can figure out who knows what, and then that way we can classify really all of our data. And so Zooniverse has this cool thing called ZooBot that they're implementing that kind of lets you make like a decision tree to decide where it should go. Another really cool thing that Zooniverse has worked on, and you can see this is actually this is a project called Gravity Spy. It's a little bit more popular than my Name That Neutrino. But this is for LIGO, for looking for gravitational waves. So this is another really interesting citizen science project. But really, when you look at Name That Neutrino, you don't have to look at the tutorial. You don't really have to understand anything that you're doing. You can just start clicking things or watching things. And so the way that Gravity Spy has their setup is that there's a locked and an unlocked level here. And so it kind of forces people to go through that like tutorial sort of phase to kind of get to the next level to make sure that you understand what you're doing. So that's what we want to do, is kind of add in maybe more of a gamified kind of thing where like, oh, you got it right, oh, you got it wrong, this is your score, or something like that, to make the users a little bit more confident and knowledgeable. But for me, I also noticed that I was like bothered that I couldn't get to this stuff, right? So I wanted to start classifying and finish this on my own. And so I think it's like some motivation also to be able to get to that next level, to level up or what have you. So I welcome you to give it a try, right? So this is the QR code to get to Name That Neutrino. It's also, you can probably just Google Zooniverse Name That Neutrino. I do want to show you the tutorial, or this little instructional video we have. Okay, it's going to be hard to hear them. So one of the interesting things I think that so my student made this also. Yeah, was that kind of like, oh man. This idea of like being able to like filter out the noise. And I think it's so interesting how our human eyes are able to do this, right? This concept that I can't get distracted by all this other stuff going on. Instead, I see this kind of clustering this like signal that's happening in a different location. And so that's really just such an interesting thing, I think, for us in this age of where AI has become so popular and so useful and amazing and everything, that there are just still some limitations and still some amazing things that us as humans completely can outperform faster, right? Can really see these kinds of things. Okay, so I just wanted to give you an overview of like what I've been working on. So really in only the past like 2 or 3 years, I've built this project called Name That Neutrino, lives on this Zooniverse website. We have over 3,500 registered volunteers. Now that's people who click the button and say, yes, register me for this project, but there's more people who go on just like maybe as a one-off or don't want to record their name or something. And that has led to over 250,000 individual classifications. And so each of our videos, we have them classified multiple times. And so we're looking at that data, trying to analyze how we can really use that, because the long-term goal here is to be able to create new data sets for IceCube. And so IceCube actually takes so much data. It's on 24/7. It's been running for like over 13 years. And so there is just so much data to weed through that in fact, we often filter out and filter and do some cuts and cuts and cuts. And our analysis level, like our level where we discovered the Milky Way, was reduced by a factor of like 20 or even higher. And so there's so much data that we aren't analyzing, but with Name That Neutrino, we'll be able to increase those data sets and really look closer at some of those things that we haven't been looking at. And so I welcome you to give it a try. And if you're interested, you can, become a registered user or, use it in your classrooms or spread the word to friends and family. I feel like it's an easy thing to do. Like it should work on your mobile device really easily, waiting for a train or something. It's a nice thing that doesn't take too much time. And it's actually really quite useful to IceCube and to me and my students as well. So thank you.
Good, thanks. This was great. Any questions?
Hi, thank you. Very basically, and maybe I missed it, but I don't understand how you detect a neutrino apart from all the others. Like, you're only getting certain events, right? Like, what makes one neutrino detectable and the rest that are coming through in the same direction not detectable?
So that's a great question. It's kind of about probability, right? So we know like an atom is made of mostly space. And so actually the neutrino coming in is going to interact with the proton or the neutron. And so it has to be close enough, right? And so you can like kind of statistically look at it and ask yourself, am I going to be able to detect, this certain one at this certain energy and actually run a simulation to figure that out. And so some of them we don't, right? We just don't detect a lot of them. And in fact, another thing that IceCube's really known for probably about 10 years ago was first detecting these really very high energy neutrinos. And we really only detect probably about 10 of them a year. And so it's just, they're hard to detect. And that's why we need such a big detector, right? It increases our chances of catching them.
Yeah, I remember that 30 some years ago in Japan, in the underground mine, like it was a big deal when there was a supernova detected, and they would have like a dozen events or something like that. Is that?
Yeah, it's so interesting you brought up a supernova because we now have this really great network of all of these different multi-messenger people, like, LIGO looking for gravitational waves, IceCube, we have optical telescopes and gamma ray telescopes. And so we have this network where it's an alert, right? So if somebody sees a supernova, then everybody gets a signal and then they're all supposed to look in the sky at the same spot at the same time so we can get data in like all of these different ways, which would increase like the number of things that we're seeing.
So is that like supernova is a practical thing for doing this? Is there any other practical science that's going to be coming out of detecting these?
Yeah, so for sure, the idea of who's producing the neutrinos can then help us understand like the astrophysics that's happening at these different events. Right, so if you're like, I know that neutrinos are being produced by this supermassive black hole. Well, are neutrinos produced by every supermassive black hole? Like, what makes that one different than other ones? Are we going to be able to get more? Is it just a matter of signal, or is there fundamentally different classes or something that we would have to figure out? Yeah.
Hi there, thank
sorry.
you for the talk, great, that was my question, so if you just asked it before class, it's another one.
Sorry, Lou.
No, that's okay, so, you know, you have this mile wide cube. The question is, if you have 68, I don't know what the number was, 68 trillion zillion going through your thumbnail at the time. What percentage of events do you imagine that you're capturing, and how much you need to know a thing to make a simile of the Milky Way or to answer other questions?
That's a good question. Let me start by saying that that IceCube is not detecting all of the neutrinos that we see, right? IceCube is targeting those like higher energy, focusing on astrophysical kind of neutrinos. So for example, our sun is a really huge producer of neutrinos, and there are some experiments that target understanding the solar neutrino and measuring that to really great detail, because that's actually where neutrino oscillations were first discovered, was studying the neutrinos coming from our sun. We were like, we're missing all these neutrinos, where did they all go? And it turns out that they were just turning into a different kind of neutrino that we couldn't detect. So we're not measuring all of those neutrinos. The other thing has to do with kind of like the statistics that we define for the problem. So if we're trying to say like neutrinos are coming from a specific source, right? So then you look over several years, like you would have to say, well, how can I be confident that that's not a background signal? And so we run all these kind of different like statistical tests to tell us that. Yeah.
Can I ask sort of a follow-up question
Yeah.
about, so do you correlate tests from a particular source with other sort of thing, a regular telescope and infrared telescope? Or
yeah, so there's a lot of studies going on with that to try to tag things together, and actually the other day we were kind of excited because there was it was one of these like real-time alerts, and we were thinking it was happening at the same time that we saw this other, but it turned out the directions weren't aligned as well. But yeah, that's what we're always trying to do is work with these other groups. And so it's a whole different kind of interesting dynamic, because all of these different people have their own collaborations that you know collect their data in their own way. And so being able to kind of figure out how much to share and how much to and how to work together and all of that is like a whole different people problem. But yeah, we're really working on that. Yeah.
I have to put a plug in for Zooniverse.
Yes.
I've been a registered user for a number of years, and they send you emails saying, here's a new project that would be interested. So about a month ago, I got an email about the IceCube, and it took me a while to go through the tutorials to get the hang of it, but I've enjoyed it. And I've learned a few more things from your talk. And just as a footnote, having been in science, I know how much effort it takes to get one data point. And when you have a whole hump of data that needs to be analyzed, you need a lot of people to contribute. So if you do an hour a day or waiting for in the doctor's office, you can do a few things. If you're retired, you can even do longer. and have fun. You're actually, you know, you're not bored. And this is just one of many projects in the Zooniverse universe.
Yeah, that's right. And for sure, I think there's a lot of really interesting kinds of projects. I mentioned a couple of them, but yeah, they don't have to be about physics and astronomy. Those are the ones I know most about, but there are all sorts of different, there was one about like historical data, actually, like reading weather, like the font was all funny in like an old newspaper, but like, of course we can read it really easily. So yeah, so there's definitely a lot of richness in these different projects. Yeah.
Hi, thank you so much for doing this. I have a couple of maybe weird mechanical questions.
Okay.
Like, how's climate affecting your research, and is drilling all of those holes destabilizing the ice shelf? You said that the water refreezes. Does it refreeze clear? And what happens when one of those goes down?
Yeah,
Like when it breaks?
so many questions at once.
Sorry, they're like all kind of related, but like all mechanical.
No, that's fine.
Do them all out there.
One of the really great things that that we can do is actually, you know, yeah, study these different things I was saying, like dark matter, do that stuff, but also glaciology is another like field that we've published papers on and looked into. So in fact, understanding what the ice looks like and how it moves and everything is part of the contributions of IceCube. And so for sure, we're trying to, yeah, better understand that field overall. Does it freeze clear? That's a great question.
I think you had mentioned that the ice was really clear down.
Yeah, I wonder if, I mean, part of it is kind of like, we didn't necessarily know what it looked like in great detail until we put our detectors down there. I think there's not any like clear signatures of like the melted hole compared to like the string. I think we would see that like as a relic in our data.
Like optically clear.
Yeah.
For it to.
Well, I think it
neutrinos don't need.
freezes. Right, exactly. But it is optically clear for us to be able to see the light that's being produced. So that is like one of the main key components. One of the things that we do also though is run regular tests. So some of these, or all of them maybe, have like little lasers on them. And so we run like every, you know, we know what the light should look like. And then we can see how well our detectors functioning. And so that's one way that we're able to see, okay, actually this one DOM is broken. And so in fact, that is like a cut, like a cleaning up of our data that we can do. Once we do know which ones are malfunctioning, then we can, you know, weed that out or address that in our analysis. The other thing, what was I gonna say?
They're like in there, you're not digging it back out.
You're not getting it back out. Yeah, exactly. So whether it's gone, but at least then we know, or it's broken, at least then we know that it's broken. You said something else that I was gonna talk about.
How's climate change affecting your work?
Yeah, so I think that goes back to the idea of just like understanding what's going on with the glacier overall. I think the other interesting thing, and I don't know anything about this, but there's a layer of dust also that we didn't know about until we started taking our data, and then we can see it in like at all, you know, all of our signals. And so I think just just like studying the ice and the layers is something that we're able to recognize. Being at the South Pole, like being on the interior, there's not any ice shelf issues on the interior of the continent. And so, yes, it's not exactly an issue.
Thank you so much.
Yes.
Can you explain a little bit about the spatial location of the detectors, vertically
Yeah.
as well as horizontally?
Yeah, that's a good question. Oh, why is that? There's like a. Yeah, thing. Yeah, so I think it's worth saying that we have, where'd it go? Here, that there are 86 strings right now, right? We're gonna add 7 more, but there are 86 right now. And so all of those 5,000, they're, you know, distributed across those 86 different strings. It's kind of in this weird like hexagonal pattern. The strings is like a vertical line. Yeah, exactly.
How far apart in a given string?
Yeah, I'm trying to do the math in my head. I don't know. So they're distributed uniformly for the most part, except for what we call deep core. And so this is the region on the most inner part of the detector where the strings are actually closer together. So the detectors are more densely populated there. And the interesting thing is that that's what we're doing with our IceCube upgrade. We're not expanding it to try to make it bigger right now. Instead, we're drilling more inside to make deep core even more like dense. And so then we can understand, you know, have a better picture, right? The more detectors you have.
Spatial.
Yeah, exactly.
Not only in the flame.
Yeah. So, right, so this is actually more like a cylinder on the inside, is where we have this. Now, that's not to say that we don't want to make it larger. So there's another project called Ice Cube Gen 2, which is about expanding it to a larger size. However, that has yet to be approved yet. And so we're in the workings of trying to see where that would be. I think the current estimate is that the drilling for Ice Cube Gen 2 wouldn't happen until like 2030 anyway. And then of course that takes long because we're only doing the drilling in the summer, the South Pole summer. So that's not really, you can't do this quickly, right?
A few questions regarding the mechanical insertion. How was it done? Few things. How was the machinery utilized that was there, or was it specially flown in? And well, we have a friend who was the mission commander on the mission that you were talking about. I think you may have referenced the one in 1999 where Dr. Jerry Nielsen had to be removed early from the South Pole because of breast cancer. Anyway, the point being, we've had some chats with him and he's talked about how very difficult it is to travel during their winter.
Yeah.
As far as the materials that were down there, were they, I guess, specially flown in? And who finances this?
Yeah. So the materials or the equipment was specially flown in, and even some of it needs to be brought on like crawlers from the coast as well. And so Ice Cube's funded by the National Science Foundation, in addition to several other, government agencies across the world. The United States is the largest contributor, both in a scientific sense, like the largest number of scientists are from the US, but also the largest amount of money came from the US as well.
Physically, how did they drill and insert the DONs?
Yeah, so that was from, so they have drills that were able to drill down, I don't know the actual depth, but far, and then it was melted, right? So then it was a hot water drill that was then melted, and so then the DOMs were lowered down, actually displacing some of the ice, and then continuously. So all of these ones that are all in the same string all like went down at the same time, spaced out equally. And then froze. Cool. Yeah.
What are the long-term plans for remediating the area or the ethical concerns? 50 years or 100 years is a very, very long time for research to be going on like that, for the technology will move on. But it sounds like all of that will be in the ice for 10,000 years. So a short time of collecting data and then almost an eternity of all of that still in the environment.
It's interesting, someone was asking me kind of like the lifetime of these DOMs, and I don't know the prediction for that, but certainly with Gen 2, yeah, and you're right, like on these different scales, like how long would this actually be there? I guess one of the really important things to note about Antarctica is that there's, this Antarctic Treaty that talks about like what you can actually do on the continent overall. And so there are several countries, involved with kind of deciding different kinds of science and what's reasonable for and what's worth it kind of for what we can learn versus what would be destructive or kind of like not well thought out or what have you. So to that point, there's like at least like these committees that like think about what kind of experiments are built and drilled there. And so I think that we really produced a new field is the other thing, is that like neutrino astronomy didn't even exist much until Ice Cube was built and able to collect data. And so the idea that there are all these different kinds of things that we can learn that just literally weren't going to be possible at the time without this detector.
How many of the modules are broken?
Oh, that's a good question. I don't know. I would guess small, but percentage-wise, right? There's 5,000 of them. So yeah, maybe, I don't want to say a number because I am on YouTube and I don't know the answer.
It may not be confined to your project only, but I remember one of the comparison charts you showed us. The left side, there was AI analysis, and on the right side was done by human access at certain aspect, right? I don't remember what it.
Yeah.
The left, yeah, can you
Yeah,
actually?
yeah, yeah. I think you meant this one. So this is the machine learning algorithm
I
here.
don't quite understand why humans are better at detecting certain things.
Well, so it's interesting you point that out because this is the second iteration where we specifically chose events that we knew the machine learning algorithm was struggling with. Right, so that was like part of the motivation for trying it like
My
this.
question is actually, foreseeable future. Actually, AI can learn from like a sample data, from our and human.
Mhm.
And then it would probably, my wildest imagination, would actually replace human participation or maybe discourage human participation. Eventually, do you see any possibility?
Well, it's interesting you frame it that way because you're right that that's another useful tool that like Zooniverse often has is the fact that we can create those training sets, like the humans can create the training sets and then the machines can learn from that. One of the, well, I was gonna say frustrating. One of the extra difficult things about IceCube is that there is so much going on, right? There's a lot of noise, there's a huge amount of data, there's so many detectors, right? So it's really quite complicated data. And so I think that there's always room maybe for like thinking about it in a different way and looking at it a different way that might require citizen users. But more importantly, I think I'll go back to the idea of that protein folding game called Fold It, where it just didn't seem like any of the machine learning algorithms were approaching the way that the humans were thinking about it or seeing it or visualizing it. So if you're asking my opinion, I do think that there's always going to be kind of like a fundamental use for citizen science in a scientific perspective, but also in an outreach perspective, right? Like the fact that we can get, 3,000 more people involved in IceCube and contributing to the project who wouldn't have done that before, I think is a really important thing just in an educational kind of outreach perspective.
We're teachers.
That's great.
Hi, thank you for giving a really nice talk. My question is, you said that IceCube could potentially be used to study dark matter, which is super interesting. Do we have ways in place to use IceCube to distinguish dark matter from ordinary neutrinos? So at some point, if you're looking for dark matter, the neutrinos become a background, right?
So I've worked on dark matter projects that have to do with shielding and understanding your signal to a great detail, right? So like you go underground and you shield everything and you tag things and you understand that this is what electrons look like, this is what muons look like. And then if I see something new that doesn't belong to one of those things, then I can say that this is a signature of and I see enough of it, right? A signature of a new particle that no one's discovered before, like a dark matter particle. IceCube is different in the sense that it doesn't have any shielding, right? Like we're detecting everything all the time. Like it's just in that energy range, like we're just flooded with data. And so it's the other kind of way. It's thinking about like more about what would a dark matter density be in a certain region, right? And what would our flux of neutrinos or flux of particles look like coming from there? But if there's dark matter there interacting, maybe taking some of that signal away, we can then say that the reason why we're not seeing the flux that we should see is because, and so these studies we've done and we've set limits on things, we haven't detected dark matter like that yet, but that's the kind of way that those studies go for IceCube.
Mostly just looking at the size of the flux.
Yes, yeah. Mhm.
Other questions?
What differentiates a neutrino that produces a detectable event from the multitude of ones that don't?
So it has to do with the interaction that produces that like light signature. And so I was kind of saying it before about like the probability of like if it's in the right place at the right, like it's close enough to have this interaction. But also it's about like how so what we're detecting are neutrinos interacting via the weak force. So it has to do with like the type of neutrino, so we could have different flavors of neutrinos. And then actually with the weak force, we have different types of interactions as well. So we have like the W and the Z bosons are like these different ways that the weak force works. And so that's why we get these different, so these are related to the weak force. And so, yeah, so we, it's not even as straightforward as it should be, where it's like 3 of these and 2 of these. It's much more complicated.
That was my follow-up question.
Yeah.
Can you differmutate between the various types of neutrinos?
To some extent, yes. So for a muon, oh, let me show you that track. So for a muon neutrino, the thing that's produced from a muon neutrino interaction is a muon. And a muon is going to be producing a track in our detector. So if you are seeing a starting track, where is that? Yeah, that is definitely coming from a muon neutrino. If you're looking instead at, okay, so these are the different kinds of weak interactions. It's either charged current or neutral current. So to some extent, yes, it's not a perfect system, but yeah, it does give us a lot of information. And in fact, this is how our simulations are produced, right? Like we feed it all of these calculations and all of these different ways that these things would interact. And that's how it produces the signals that we then can compare to our data as well.
Thank you.
Thanks for that. I was wondering what's the advantage of doing this underwater at the South Pole versus say a deep mine or something like that? Is it the depth? I mean, you need something dark, I guess, in order to see the optical signals or whatever, but is it the amount of
So I guess it depends on what you're trying to do. So if you're looking for like dark matter, then you would want to go underground and shield. But because we're able to see because neutrinos are able to just go through anything here, like we're able to see the neutrinos, kind of no matter what. So we don't have any like shielding built or anything around this detector. One of the interesting things that's coming up with like KM3net that's currently being built in the Mediterranean Sea, which uses water as its detector medium, as opposed to ice that we use at the South Pole, is that there's like animals and waves, bioluminescence is one of our favorite things in Ice Cube to joke about. They're actually just seeing animals creating this light. And so there's like a whole lot of different kinds of instrumentation issues and just understanding your environment that you're in. Yeah.
Take a hell of a tank.
Right, you could use a tank. That's right.
Just out of curiosity, how much does the South Pole move per year behind the glacier relative to the pole?
Oh, you know what? The winners over said this. No, I think it's centimeters. I don't think it's much. Or maybe a meter or something. So like they can look and they say, oh, there's where it was, and now we need to move it like over here. So it's like, it's not too bad. And in fact, they were talking about this thing that they do. It's called the Race Around the World, where they have a 2-mile race around the poles. And this is like they keep actually, they have like a ceremonial pole that was like, like an original kind of pole. And then they have every year they put a pole for the new geographic location as well. And so they do this race. At this point, I don't know if they add more to make it 2 miles, but yeah, so that's where they are.
So you run 2 miles east, go around the world, and you return to the same point?
Yeah, you did it. I mean, you could even do it like faster, but.
Great. Any other questions? All right. Let's thank Christina for the great job.
Oh, I do have stickers up here. If anybody wants Ice Cube or Name the Neutrino stickers. I also have some other pictures from the South Pole. if anybody's- Yeah, thank you again.
That was really wonderful. Thank you so much. That concludes our,
Yeah, please.
that concludes our,
Would you put up the standard model?
that concludes our meeting. But thank you all for coming, and if you have your eye on something on the back table, make us an offer and we'll probably accept it. We'll see you all soon, and we'll see many of you, I'm sure, at the visitation for Lou next Tuesday from 5 to 7. Bye, everyone. Goodbye to everybody on YouTube.